Shall we start?
Yes, sir.
Okay. Actually, there is a problem in network. So is my screen visible?
No,
Hello?
sir.
No, sir.
Not visible?
No, sir.
Yes, sir. Now visible.
Okay. So today we actually discuss start from Hamilton's principle. Mm. We already discussed about Lagrangian formulation. In Lagrangian formulation, we first calculate generalized coordinate Q, then generalized momentum P, which is called conjugate momentum P, and then calculate Lagrangian as a function of also calculate generalized velocity q dot, and we express Lagrangian as t minus v. L is equal to t minus v, and in general, T is a kinetic energy, which is half m q dot square, and V is potential energy. So Lagrangian is a function of both q and q dot. So L, actually, if you write, L is nothing but a function of q and q dot. Okay. And q dot means position coordinate and velocity coordinate, or generalized coordinate and generalized velocity. Q dot is dq by dt. Okay. Lagrangian is a function of q dot. It may be a function of time, but
Sir,
for
this is MPH6.
hello.
So this is MPH6 today you are teaching?
SS MP6.
Okay, sir.
Like the Hamiltonian formulation, then all about Hamiltonian. Huh? We start from Hamiltonian formulation.
Okay, sir.
Okay. Um, So we already know Lagrangian is a function of q dot t. Q dot means kinetic energy, half m q dot square. Potential energy may be a function of q. Uh, and the space where we solve this problem related to Lagrangian is known as a configuration space, because here we can define the configuration completely by using generalized coordinate. Another space, uh, but we now know momentum is related to coordinates, uh, and it's called conjugate momentum. We can define a space, position and momentum taking as our coordinate. Actually, for a system of n particles, there are 3n number of position coordinate. 3n for one particle 3 xyz. So second particle again xyz. So if n particle, it has 3n degrees of freedom, or 3n q coordinates. Correspondingly 3n momentum coordinates. So if you add with 3n position coordinates with 3n momentum coordinates, then we have a 6n dimensional space. And that space is actually known as phase space. Space in QP, position and momentum. Okay. So phase space is a 6n dimensional space, where the path defines the actual path of motion, because actual path means we define its q and p momentum related to energy. So once you know its exact position, exact energy, then path will be exact. Okay, that is the phase space. And so Hamiltonian formulation is done in the phase space. All are written there, you can learn it. Okay. Now Hamilton's principle. Uh, Hamilton's principle is applicable to all monogenic system. Monogenic system, we know conservative system. Conservative system, force is negative gradient of potential. But in monogenic system, force can be taken written as the negative gradient of potential, where potential may be a function of position or velocity. For conservative system, potential is only function of coordinate. But for a monogenic system, potential may be a function of velocity. Okay. A conservative system is a subset of monogenic system. According to Hamilton's principle, for any monogenic system, Hamilton's principle states that uh, the motion of a system from time t1 to t2 is such that the line integral, which line integral I is known as also action, integration of L dt from time t1 to t2 has a stationary value for the actual path of motion. This is Hamilton's principle. According to Hamilton's principle, for monogenic system, you can write conservative system. Hamilton's principle states that the motion of the system from time, suppose system is moving from time t1 to t2, here is 1, here 2. Motion is such that the line integral to be a constant. So its variation is 0. If it is constant, then the variation delta is 0. Okay? Hello?
Yes, sir.
Okay. So now from this principle, you can also derive the Lagrange's equation of motion. Before doing that, we have discussed some techniques of the calculus of variation. Actually, this is just one kind of least action principle, what you know in your optics or other places also you know least action principle. The integral is called action, and action minimum means least. Least if least value, so its variation is 0. So for this, let us consider a general thing. Instead of Lagrangian, let us consider any function j, which is a function y dot x. Is consider its a position coordinate, y dot is velocity. He and x is the variable. Here actually Lagrangian q dot t. So q dot means our case dq by dt. But here thing is dy by dx. Uh, So according to our Hamilton's principle, integration in place of L, I have to write j dx should be minimum. Also delta variation should be 0 for actual path of motion. Now let us consider a large number of passes between 2 points. If 2 points are given, we know it can large number of passes are possible. For actual path, we have this condition. So let's say for actual path is yx0 and any other path nearer to it can be explained through a set of equations yx alpha is equal to yx0 alpha eta x. But all paths should pass through this endpoint x1 and x2. Okay. So this means our variation eta x, it is 0 at x1 and 0 at x2, which is known as eta x1 0, eta x2 0. Okay. So our general expression is yx alpha is yx0 plus alpha eta x. Exact path may be yx0 and the deviation, but whatever may be the deviation, at the endpoint it must be give same value. So at the endpoint eta x1 0, eta x2 0. Okay. So now this is your j, but delta j, when we know when f is a function of x, y, z, then df is equal to del f by del x into dx, del f by del y and dy plus del f by del z and dz. Similarly, since j is a function of y dot x, we can write delta j is equal to del j by del y delta y, del j by del y dot and del y dot, del j by del x and delta x. J is your function. Now calculate it's because your parameter is alpha. Alpha is varying for different paths. We have to calculate the variation of j with respect to alpha. So we can write this. We know it delta j here. and then delta j by del alpha. So it will be del j by del y into del y by del alpha, del j by del y dot by del alpha plus del j by del x and dx by del alpha. Is not it? Hello? Are you getting my point?
Yes, sir.
Yes, sir. Okay. So now we from this we can derive Lagrange equation. Let us for simplicity consider a one-dimensional problem. One-dimensional problem, 1x. Another is x dot and the t. In one dimension case. So for our case j, which is a function of y dot x. Now compare it. We know delta j is equal to 0. This is written. So our general path will be yx alpha is equal to yx0 plus alpha eta x, and same condition at endpoints x1 and x2, eta x1 0, eta x2 0. But we did now we reduce it to a one dimension. All these things. So j alpha integration of f y dot x delta j is equal to 0, but we have to calculate del j by alpha, and for actual path it should be 0 because delta j is 0. For actual path delta j is equal to 0, so the variation must be 0. So for alpha 0 means actual path delta j del is 0. We have to calculate del j by del alpha. Like previous case, I written del j by del alpha must be equal to if it is a function of f y dot x del f by del y dy by d alpha del f by del y dot dy by del alpha del f by del x dx by del alpha. Okay. So del j by del alpha is equal to this x1 to x2 del f by del y by del alpha plus del f by del y dot by del alpha. But x and alpha are independent parameters. As per our definition, we get x separate from alpha eta x. X and alpha are independent parameter, so its partial derivative is 0. X does not depend on alpha. So we have only two terms, first term and second term. Where y dot means dy by dx. Now integrate the second term. Now solve it this second term. Integrate it by using by parts. Okay, it is basically dx del f by del y dot del y by del alpha. So we take del f by del y dot as a first function, and this is second function. First function integration of second minus derivative of first integration of second. By parts. So this we found this is our expression. But look at this term dx dy dot by d alpha. Dx dy dot by d alpha. If we integrate it, actually it becomes dy dot means dy by dx. So it is dx del by del alpha dy by dx. If I interchange alpha x, they are independent parameter, so it will be d by dx del y by del alpha. So dx can be cancelled inside the integration or the inverse chain rule. We only found it will be del of del y by del alpha. Okay, that means the integration means del integration cancel. It is nothing but del y by del alpha. And limit is x1 to x2. Hello, is it clear?
Yes,
It's
sir.
simply integration. Yes, by. Yes. Okay. So we put this value x1, x2, but we know that at endpoints all paths should match. Eta x1 is 0, eta x2 is equal to 0. You know. So we use that. Actually, that integration vanishes. Okay. Okay. Now we put this value of expression alpha is equal to first term into this because this one in by cross integration first term integration of second, from integration of second we got this what here derivative of first integration of second. Okay. Whole term is given, and now del y by del alpha at x1 and x2 it actually vanishes because at endpoints it is eta x, because the definition y is y plus eta x alpha. So you take a derivative with respect to alpha, eta, eta vanishes at endpoints. So this result vanishes. It will be 0. Okay. So del y by del alpha at x1, x2 is 0. So we have only one term, the second term. So dx by ds is equal to minus dx by dx del y by del y dot del y by del alpha. All are written here. So our final dj by d alpha becomes this. If you see, there is a common term inside the bracket. Del f by del y dx by d by dx of del f by del y dot. So if for exact path this is 0 and for putting alpha is equal to 0, this becomes 0, which implies the integration must be 0. Since it is an arbitrary integration, the bracketed term should be 0. So we got a condition del f by del y, all written here is 0. So if it is 0, the bracketed term must be 0. D bracketed term is df by del f by del y minus d by dx del y by del y that is 0. This equation actually known as Euler-Lagrange's equation. If you put in place of f L and y is equal to q and x is equal to t, then it becomes Lagrange's equation. If we take, so general expression is known as Euler-Lagrange's equation, but if you take f is equal to L, y is equal to q and x is equal to t, then it is known as Lagrange's equation. You can check it. If f y l y q and x is equal to t, then we got right Euler Lagrange's equation. Simply Lagrange's equation. So it will be what? Del L by del Q minus d by dt of del L by del Q dot is equal to 0, which is our Lagrange's equation. Okay, I written here. So substituting these conditions, we can get x is equal to t, y is equal to q, f is equal to L, j is equal to L. So we got the equation which is known as Lagrange's equation. Okay, so also we can derive by following the procedure, putting only L there. We follow the same procedure. I will repeat this procedure. I'm putting L only. Or you can directly write here this and we got Lagrange equation. It's okay. Sometimes it asks derive Lagrange equation from Hamilton's principle. Follow that. Okay, I'm not repeating that. There are few actually examples. So what we learn here, if integration of f dx over t1 x1 to x2 is 0, then there is a condition comes del f by del y minus d by dx del f by del y dot is equal to 0. We can use this condition to solve many problems. But simplest problem is uh, the dimension of this action term, actually the action term of dimension, it is LDT. Lagrangian will be not into time, which is nothing but Planck's constant. By using this, we can find the shortest distance between a plane. What is the shortest distance between 2 points? Let's say sometimes this is asked in your examination. What is the distance between 1 to 2 in a plane? Okay, plane means 2 dimension. There are 2 coordinate x and y. So for this, we let us consider a arc length ds as you can see here. So obviously, since it's 2 component, x component, y component, so ds square is equal to, is just like a x component and y component, just like a triangle. So we can say ds square is equal to dx square plus dy square. That means ds is equal to square root of dx square plus dy square. Okay. Now taking common dx, we can write 1 plus dy by dx. Putting y dot is equal to d by dx, we can write dx in 1 plus y dot square. Now integrate for exact part, it will be integration over 1 to 2. So for complete plot, we integrate ds over 1 to 2. Integration 1 this. But we know that from definition, uh, if I is equal to f y dot x dx have part or minimum or stationary, then d by dx del f by del y dot minus del f by del y should be 0. What we got from the variation of calculus. So this is minimum means it obeys the equation. F is what this term is square root of 1 plus y square. put in place of f 1 plus y dot square, we found del f by del y 0, del f by del y dot is equal to like this in derivative. So putting the equation, we got d by dx y dot plus 1 is 0 is 0. So d by dx y dot by 1 plus y dot square 0 means bracketed term is a constant. Y dot a constant, squaring both sides we get this, and simplifying this we found y dot is a constant. Since y dot is dy by dx, so dy by dx is a constant, so y is integration of dx plus a constant ax b. So we found a final equation y is equal to ax plus b, which is nothing but the equation of a straight line. Clear? Hello, it is very important question. Hello, is it clear?
Yes,
Okay.
sir.
Another is a minimum surface of revolution. Uh, we revolve a curve x to y2 around y-axis and surface of revolution. We have to find the curve which surface of the revolution revolved surface would be minimum. Okay, it is another problem. But consider to revolving xy completely. Simply we revolve the arc length around the y-axis. Okay, whatever uh, we calculate first it, then integrate from x1 to x2. Okay, this is the procedure. So consider three. Uh, the revolves of an arc length ds around y-axis. Uh, the distance of the y-axis is x. Let's consider the distance of the strip from y-axis. The distance is x. So obviously the area is 2 pi x, and the strip strip area is ds. Okay, so our total area surface area will be 2 pi x into ds. For complete, I integrate 1 to 2. But ds again we know dx square by ds square root over, which can like previously written as dx in 1 plus y dot square root over. Where y dot is dy by dx. And when I put all this value in place of ds, then we got I is equal to 2 pi x 1 plus y dot square root over dx. Okay, but we know the rules. If it should be minimum, then it should satisfy the equation d by dx del f by del y dot del f by del y. So here in place of x we have 2 pi x 1 plus y dot square root over. So putting this 2 pi 1 plus y dot square root over, uh, found del f by del y and del f by del y dot. If you count, it does not contain y, so del f by del y is 0. Del f by del y dot you calculate like this. So del f by del y dot is equal to 0 because this term vanishes. So finally we only if it is del f by del y dot is 0. Del f by del y dot is this. Sorry. Del f by del y dot is this. Putting it around d by dx of del f by del y dot is equal to 0. Okay, solve it. This 0 means the bracket term should be constant. So derivative of constant is 0. So if constant, now squaring both side equating, we found y dot is equal to a by x square minus x square root over, or y is equal to, if you integrate it, it gives you a cos hyperbolic inverse x by a. So it's the result. If you simplify, y minus plus a constant. So y minus b by a is equal to this. We found x is equal to a cos hyperbolic y minus b by a. It is actually equation of a catenary. Okay, this problem is very important. Sometimes asked, but system problem. It is very lengthy process. The minimum time of fall. A body is falling freely from a point. Find the path for which the time covered should be minimum. So that, okay. For this, actually, we can our aim is to count the time, but arc length is a ds, and we know velocity is equal to displacement by time. D. dt. So dt will be ds by v. If we know the velocity, putting this, we can calculate the time. The time will be integration of ds by v. Calculate v. V is energy conservation equation. We know that total energy is always constant. At one point, at the starting point in total energy, it was uh, kinetic, where motion and potential. And we know potential energy is converted to kinetic energy. But much potential is stored in the system, it is converted to kinetic energy. Because mechanical energy is conserved, always P plus V in a conservative system, it is a constant. Uh, Free fall also calculated in plus 2 that at each point total energy is conserved quantity. Now whatever energy stored here actually what? It is at some height, so it is energy mgy potential energy. At the cost of this energy is moving here, half mv square. So half mv square must be equal to mgy depending on this height where it is. Half mv square is equal to mgy. So equating this, we found v is equal to root over 2gy. So our integration becomes ds by 2gy root over. Okay. So solving this also similar way we can solve it. Uh, ds is dx square plus dx square root over. Equating that we can solve the problem. This is the problem, but procedure is this one. Hello, it's okay. Hello.
Yes, sir.
Yes, sir.
Okay, okay. So this is all about first part. Then we go for second part. So we go and downloading sometime. Please 2 minutes and I'm downloading the material. Have we discussed one other step? Hello. Think not.
Sir, your voice is not audible properly.
Okay. Have we discussed neither term? I think no. Okay, okay. I'm trying to get problem in network. Okay, I'm seeing what can do.
Sir, Noether's theorem.
Neither theorem. conservation terms and symmetry. Discuss. Okay, leave that. We will discuss other things. Then go. Okay. Is my screen visible? Hello.
No, sir.
No,
Not
sir.
visible.
Yes, sir.
No, sir.
Now we good.
Phase space configuration, sir. Is it visible?
Yes, sir.
Yes, sir. No, sir.
Yes,
Okay.
sir.
Okay. And there is a problem of network. Yesterday, due to Kala Vaisakhi.
Sir.
Okay. So there is actually difference between phase space and configuration space. What I told. In phase space, Hamiltonian formulation is discussed in phase space, and Lagrangian formulation is configuration space. Okay. In configuration space, there are many paths are possible between 2 points, but in phase space, only we have one path, which is the exact path of motion. Okay. Now, next thing is Legendre transformation and Hamilton's equation of motion. We got that. I think neither not discussed. So I first discuss that because there is a term. Have you calculated? I think yes, Hamiltonian from Lagrangian. I think calculated. Hello. Actually, we
Yes,
have
sir.
calculated Hamiltonian from Lagrangian. H is equal to summed over qj dot minus
Yes,
L.
sir. Yes, sir. We have
Uh,
covered that.
we calculated. Okay. We covered that. Okay. Now we use here. Okay. So actually, Lagrangian is a function of q dot t. What I have already told. For coordinates, velocity, and time. Lagrangian is a function of q dot and t. But Hamiltonian, we have calculated phase space. Phase space means position momentum space. What we saw? QP state. Phase space. Phase space means it is QP state. Position momentum space. So Hamiltonian is a function of basically QPT.
Sir, we have studied this Hamiltonian in MPH-2 also. Is it there in MPH-6 also?
Yes, here Hamiltonian formulation. That is only we calculate Hamiltonian, but here Hamiltonian canonical equation of motion. Okay, using that we solve different Hamilton-Jacobi theory. All are written in the syllabus.
Okay. Okay, sir.
It was written legendary transformation. We are written in our syllabus. So remember this thing. Lagrangian is written in the form of function of q dot t. Hamiltonian is qpt. So there is a, if you compare these coordinate systems or basis, you can say, you see here q dot, here p. You know it. Other things are same, q same, t same. Only q dot is changing to p. We have an expression h. You remember we calculated Hamiltonian from Lagrangian. H is equal to summation of Vj Qj dot minus L. Is not it? We have written summed over J Vj Qj dot minus L. Vj Qj dot minus L. Okay. Lagrangian is a function of Q dot. Hamiltonian is a function of Qp. But relation is H LV relation Pj Qj dot minus, which actually changing between Lagrangian and Hamiltonian. Qj dot is Pj. Actually, that type of transformation is actually known as Legendre transformation. What we see in terms of thermodynamics, when we relate to uh, functions, which have basis, in basis only one coordinate or one set of coordinate is different, like Lagrangian is q dot, Hamiltonian that is pj, and we found h by subtracting that term, the product term qj dot pj. For example, so now if you write L q dot t qj dot cancel, so final result is a function of pj qj t. Clear? That is the main thing of Legendre transformation. Now for that we consider a simple function. Let's consider a function f. F is a function of xy. So df is equal to del f by del x into dx plus del f by del y into dy. Okay. So let del f by del x is u dx plus v dy. U is related as del f by del x, v is del f by del y. Here also we have some relations. Pj is equal to del L by del qj dot. We know that. There's some kind of relation. Now set another variable g, which is function xy minus ux. Here from basis we change x by u. So my g will be final function of y and u, like here. Finally, if I substitute this g is equal to f of xy minus ux, then I find dg is equal to df minus dux, df is udx plus vdy minus udx vdy, udx cancel. So it will be final vdy minus x du. That is, g is a function of uy. So from x, xy to I come g uy, changing x to u just by subtracting the product ux. That transformation is known as Legendre transformation. Same thing is happening here. I just getting Hamiltonian from Lagrangian by just subtracting Lagrangian q dot p. It's a minus sign here, a minus of this q dot p, product of q dot p. Hello, are you getting my point?
Yes, sir.
Yes,
Uh,
sir.
Yes, sir.
which was changing, that will be product for the two variables separate. So dg is final this. Okay. If you write this, so going from Lagrangian formula to Hamiltonian formulation, we have a change of basis from q dot to qpt. So following above procedure, we can change get this. So Lagrangian is the function of q dot t. So dl is equal to, if we follow f is a function of x y z, df del f by del x dx, del f by del y dy, del f by del z dz. So it will be like this: del L by del QZ dot DQZ del by DQZ and del by del T dt. But we know Pj is equal to del L by del QZ dot. We already know from MPH-2, Pj is equal to del L by del QZ dot. Putting that, we found d by dt of del L by del QZ dot minus del L by del Qj is equal to 0. But this is Pj, so del L by del Qj is equal to Pj dot. This is Lagrange's equation. In using this in Lagrange's equation, we found Pj dot is nothing but del L by del Qj. Okay. But dl is equal to, here we have expression. So in place of del L by del Qj, now I write Pj, the del L by del Qj, Pj dot, and del L by del Qj dot Pj, using two equations here, one and this one. Using this, I found this expression. But from relation, we have h is equal to sum over Pj Qj dot minus L. So expanding it, dh is equal to qj dot dpj plus pj dq dot minus dl. Again put dl. dl is a function of q dot t. So it has also three terms. So if you compare, actually one thing cancel, q dot dpj. It's a p dq dot p dq dot. This is cancelled. No, sorry, sir. This not this one. Third, this one. Second and fourth. Pj dqj dot. Now here is a pj dqj dot. This is cancelled. So it is a function of qj qj t. Comparing this, okay, these two equations, actually We got del ds is equal to del h by del qj dqj, del h by del pj dpj dot, and del h by del t dt. Okay, it is pj. Huh. It is not that pj. H is a function of qj pjt, so dh is equal to del h by del qj dqj plus del h by del pj dpj plus del h by del t dt. Now compare with this. Is also the same ds left hand side, so right hand side must be same. So whatever multiply here with dqj, it must be equal to whatever multiply with dqj. What multiply pj dot? So we got pj dot is equal to del h by del qj minus, there is a minus sign. So pj dot is equal to minus del h by del qj. Similarly, compare the coefficient of dpj. Del h by del pj. So del h by del pj is equal to qj dot. Okay. And compare third term, del h by del t is equal to minus del L by del t. We got this set of equations which is known as Hamilton's canonical equations. There are actually 3nj and 3nj. So for qj we have 3n equations, for pj we have 3n equations. A set of 6n equations. 6n equations that are known as Hamilton's canonical equation. Hello, is it okay?
Yes, sir.
It is also very important. It is simpler. You see,
Yes.
all steps are done here. Very easy, not difficult. Comparing the coefficient. So we got Hamilton's equation. Uh, so it's known as canonical equation of Hamilton or Hamilton's equation of motion. There are first order differential equation, Lagrange's equation, second order differential equation. For here, first order differential equation. One derivative. And sometimes has so that the coordinate is cyclic in Lagrangian, it must be absent in Hamiltonian. Cyclic means it does not appear in the Lagrangian. If Qj does not appear in Lagrangian, we call it cyclic coordinate. So del L by del Qj 0 if L does not contain Qj. So that del L by del Qj is equal to Pj dot. So we got Pj dot is equal to 0. But now for canonical equation, we found Pj dot is equal to del H minus del H by del Qj, which implies del H by del Qj 0. So H does not contain Qj. The one the question sometimes asks, so it you can show like this. Okay. Again with some equation which is known as Poisson bracket of two quantity. On that term we also derive the relation. Okay, where is that? Have I discussed or not? There is a bracket known as definition Poisson bracket. Poisson bracket of two quantity UV with respect to QP can be written as summed over J if there are many number of variables. If one variable, then del U by del Q, del V by del P. If there are many variables, summed over J, del U by del Kj into del V by del Pj minus del U by del Pj into del V by del Kj, which comes first UV Poisson bracket. So UV Poisson bracket will be summed over J del U by del Qj into del V by del Pj minus del U by del Pj del V by del Qj. Okay. So in place of if you take Qj Pj, this is wrong. Not what is it? Now in place of U put Qj. In place of V you put Pj. So what you got? Del Qj by del Qj 1, del Pj by del Pj 1 minus 0. So if they satisfy this equation Qj Pj is 1, if they are different Qi Pj, I Pj, so it is delta Ij. If Ij are different, then they are obviously delta Ij. Okay, this is a definition of one kind of bracket, Poisson bracket, which actually used in canonical transformation. We discussed in the next class. But before that, you remember a formula that is for Poisson bracket. In place of U, you can put in one variable. In place of V, you can put one variable, and Poisson bracket calculate from this formula. Okay. For simplicity, let us consider an example problem. Poisson bracket of R and P. R mod and P mod. R is a vector, position vector x I cap, y j cap, z cap. Its mod will be x square plus y square, z square r. P, its mod will be px square plus y square, z square. So how many coordinates are here? Here actually x, y, z, correspondingly px, py, pz. So three set coordinates. J varies from 1 to 2, 3. 1 to 3. 1 xpx, y py, z pz. So correspondingly, this formula becomes according to this definition. Okay, according to this definition, some means some or x, some or y, some or z. Del r, our u in place of u r mod, in place of v p mod. So del r mod by del x px pxx. Then y py. Okay, z pz. Are you getting my point? It is very important. Hello.
Yes, sir.
Huh.
Yes, sir.
So how many coordinates? It is three coordinates. So three set. J varies from 1 to 3. So then calculate individually what value. R is given, mod is given, del R by del X is equal to X by R mod. Similarly, del P by del X with Px by P mod. Okay. So R mod putting all values, we found this. X Px by R P mod, Y P by R P mod, Z P Z. X Px, Y P Y plus Z P Z. It is actually nothing but dot product of R dot P. Okay. A dot B means XBX plus AYBY plus AZBZ. So R dot P dot product by its magnitude means it's only vector part R cap P cap. So result will be R cap P cap. You can do other problem also. Suppose simple example, find the Poisson bracket of two quantity. Q is given Q plus 4 alpha P, V is equal to Q plus 2P. Find a canonical conjugate. Actually, we discuss in the next class. Canonical conjugate means we have to check its Poisson bracket. It should be 1. If Poisson bracket of two variable are 1, then we call their canonical conjugate. Okay. So if Poisson bracket of two variable is 1, QP Poisson bracket is 1. So they are called canonical conjugate. If you put to U plus QP, then always 1 into 1 and this 0 1. So QP are canonical conjugate. Not only QP, any two functions, if they are if canonical conjugate, then their Poisson bracket must be equal to 1. So given question that they are canonical conjugate, that means Poisson bracket is 1. Find the value of alpha. Okay, you have to use formula del u by del k, del v by del phi. Here only one set of variable. Generally question asks for one set of variable. So 1 means only one del u by del q, del v by del phi minus del q by del phi, del v by del q. If you put uv, we found del u by del q 1, del u by del phi 2, and del u by del phi 4 alpha, del v by del q 1. So this, so alpha is equal to 1 by 4. So if it is canonical conjugate, alpha should be 1 by 4. Another very important problem, I think it is asked last time. This is find this a transformation PQ to capital PQ is canonical. Canonical means again Poisson bracket of capital PQ is 1. Small PQ is 1 by definition, but it goes from small PQ to capital PQ. It should be canonical if its Poisson bracket is 1. So a canonical given means its Poisson bracket 1 is given. We have to find the value of alpha and beta. QP is given like this. So we have to find QP is equal to 1. So Q value is Q is given, capital P is given. Put using this formula del capital Q by del Q, del P by del P minus del Q by del P, del P by del Q is equal to 1. Taking derivative, we found this. Taking common this quantity, we have this is cos square sin square 1. So this one means what? Here power of Q and constant. So it means there is no Q pair. So we understand that there is no power of Q means here power of Q power is 0. So compare with power of Q and coefficient. Power of Q is 2 alpha plus 1. So 2 alpha plus 1 must be equal to 0. That means alpha half. Again alpha beta must be equal to 1. So beta is equal to 2. Okay. Hello?
Yes, sir.
This type of question asked in your examination if you still asked a question. Poisson bracket. Huh? So formula is this.
Yes.
Yeah, you Poisson bracket is 1. Whatever given function, that Poisson bracket must be 1 if they are canonical.
Sir, alpha minus 1 by 2 or plus 1 by 2?
Sorry. Here 2 alpha minus 1 is equal to 1.
Minus.
So
Okay.
alpha is minus 1 here. Power is minus 1. Okay. So if alpha plus Then 2 half cancel 1 minus 1 is equal to 0. Power is 2 alpha minus 1. Okay?
Okay, sir. Understood.
Then this is another problem. So that these are canonical conjugate. You have check. Canonical conjugate means we have to check uh, QP Poisson bracket must be 1. If 1 canonical conjugate, if not, then not. So first case actually found it not, but in second case it is 1. So second is a canonical conjugate. Okay. So now we can write the Hamilton's equation in terms of canonical conjugate. Okay. Where is the thing? Here. So we know that H is a function of Qj Pj t. So dH del H by del t is equal to del H by del Qj into Qj dot means dQj by dt. Del H by del Pj into dPj by dt plus del H by del t. So Qj dot Pj dot d. Uh, but Qj dot according to Hamilton's equation it is equal to del H by del Pj and Pj dot minus del H by del Qj. Putting that we have this equation. So their actual first two term is just like a Poisson bracket of u and h. So derivative of any function can be written as Poisson bracket of that function with Hamiltonian plus its partial derivative. So du by dt is most equal to uh or del u by del t. Okay. If it does not contain time explicitly, then we can remove this term and this uh is equal to du by dt. So if u is a constant, then du by dt is 0. So Poisson bracket is 0. If it does not contain time explicitly, explicitly means directly, it does not contain time. So okay, so what I have written there, if Hamiltonian does not contain time explicitly, does not contain time explicitly means its partial derivative is 0. It does not contain, suppose s is a function of qp only. Q may depends on t, p may depends on t. That is implicit dependence. If s directly contain t, then we call explicit dependence. Its partial derivative is non-zero. If does not contain directly, then partial derivative is obviously 0. So this condition what I say, if u is a constant of motion, then du by d 0 or uh is equal to minus del u by del t. If u does not contain time explicitly, then is 0. Sometimes question asks, so that is a constant of motion. You have to take its Poisson bracket with Hamiltonian. Okay. But we know Q, P are independent coordinate. They are not uh, QPT, we are taking three are independent coordinates. If they does not contain Q directly T, then our Qi dq by dt must be QH plus del Q by del Q by del T 0. So Q dot can be written as QH Poisson bracket. P dot is written as PH Poisson bracket. Okay. Dot. If you take it the dot, if this one is 0, then obviously this is Poisson bracket of that quantity. So these things are also called the Hamilton's equation motion in Poisson bracket means Q dot del H by del Pj, it is Hamilton equation. P dot minus del H by del Qj, Hamilton's equation. But Q dot H according to Poisson bracket is QH Poisson bracket is equal to Q dot Qj dot. But here Qj dot del H by del Pj. So in if question asks write Hamilton's equation in terms of Poisson bracket, you have to write Qj dot is equal to Poisson bracket of Qjh. Similarly, Pj dot is Poisson bracket of Pjh. Okay, these are known as Hamilton equation in terms of Poisson bracket. Qj dot Pj dot, how you write it? In Poisson bracket term, it is Pjh, Qj dot Qjh. Okay. On these things, then Raoult's procedure. Actually, there is a procedure known as Raoult's procedure to solve problems of involving cyclic coordinates. Cyclic means it does not appear in the Lagrangian. Uh, Raoult developed a procedure to solve those problems using Hamiltonian formulation. Because if that is cyclic, then it also does not appear in the Hamiltonian. But in Lagrangian is a Q dot T. Hamiltonian QPT. If Q does not appear, but Q dot appear. But if here Q is not appear, then del H by del Q is 0, but del H by del Q is equal to Pj dot. Pj is a constant. So if Q is not appear, P is also a constant, does not appear in the equation. So one coordinate is reduced in Hamiltonian procedure. So Raut to apply this to solving problems by developing a term known as Rauthian. Okay, and this is a Hamiltonian procedure involving cyclic coordinates. So Hamiltonian formula is mainly useful for cyclic coordinate because okay, here written here in Hamiltonian coordinate we have Qj Pj. If Qj does not appear, then Qj dot may appear. But if Qj does not appear, del H by del Qj is 0. So del H by del Qj is equal to Pj dot. Pj dot 0 means Pj is a constant. So this it becomes a constant and not a parameter. That is the procedure. So right, Rauthian assume that if the cyclic coordinates are Qs plus 1, Qs plus 2, Qn, and non-cyclic are Q1 to Qs, then a Rauthian can be constructed, which is a function of Q1 to Qs, then Q1 dot to Qs dot, Ps plus 1 to Pn into T. Because Qs plus 1 to Qn are cyclic. Actually, it contains Q1 to Qn, Q1 dot to Qn dot. If Lagrangian, if Hamiltonian, Q1 to Qn, P1 to Pn. But some are cyclic, Qs plus 1 to Qn. Cyclic means it does not appear in the Lagrangian. So it will already removed. So we have only Q1 to Qs. Again, for cyclic coordinate, we use its momentum because its momentum are constant. Non-cyclic have the velocity. So velocity Qs dot, cyclic Ps1 to Psn, which is nothing but if you write this is Pj Qj dot minus L. If j is equal to S1 to n, because S1 to n Pj Qj dot. Qj dot S1 to n, Pj dot S1 to n minus L. Or we call it Hamiltonian of cyclic minus Lagrangian of non-cyclic. So Rauthian R is nothing but Hamiltonian cyclic minus Lagrangian non-cyclic. Okay, which is actually sum of j is equal to S plus 1 to n, Pj Qj dot minus L. This is Hamiltonian formula, Pj Qj dot minus L. L here contain all 1 to n, but S plus 1 to n comes under Hamiltonian and other comes under no Lagrangian. Pj Qj dot on cyclic on Hamiltonian, then on Lagrangian. Okay. So this is R. This is R is a function of this quantity Pj Qj dot minus L. So taking its partial derivative dr, dr is equal to sum of Pj dqj dot plus qj dot dpj minus dl. Okay. But dl is again del L by del qj dot dqj, del L by del qj dot dqj dot, and del L by del t. So R can be, dr can be written like this, and comparing the coefficient Pj dqj dot qj dot dpj minus del L by del qj, del L by del dqj dot. Other two are del L by del qj, del L by del t. One cyclic, separate cyclic and non-cyclic part. Cyclic part means 1 to S. Non-cyclic is, sorry, non-cyclic is 1 to S. Cyclic is S plus 1 to N. So this is for cyclic coordinate, and this is for non-cyclic coordinate. Okay. So if this is the procedure, then finally we got the Lagrange's equation d by dt del L by del Qj dot minus del R by del Qj is equal to 0. This is true for non-cyclic coordinate. And for cyclic coordinate, we use Hamiltonian equation taking H is equal to R. So main motto is cyclic coordinate obey Hamiltonian equation, non-cyclic coordinate Lagrangian equation. And we take R in place of L for non-cyclic coordinate, and we take R is equal to H for cyclic coordinate. Okay, this is the procedure. From this procedure, we can solve Kepler's problem, because Kepler's problem we will know potential is equal to minus k by r, and it's a total Lagrangian is equal to half m r dot square plus r theta the square plus k by r. If we set Rauthian, actually here theta is a cyclic coordinate. One coordinate among r theta, theta is cyclic. So according to our cyclic coordinate and its momentum, p theta theta dot minus l. This is your Rauthian. Okay. Hello? Are you getting my point?
Yes, sir.
Yes, sir. So from this Rauthian, cyclic coordinates is theta. For theta, we use Hamilton equation. For r, we use Lagrangian equation. Okay. For r, non-cyclic one r, Lagrangian equation in terms of r, where l is equal to capital R, and theta coordinate is equal to Hamilton equation, h is equal to capital R. Okay. Within this, we find Lagrangian. There is a derivation of Hamilton's equation from a variational principle. We know from Hamilton's principle, it is a for exact path of motion, it is stationary, so its variation is 0. Now, but in place of L, put this. We know H is equal to sum of Pj Qj dot minus L. From this equation, we can write L is equal to sum of J Pj Qj dot minus H. Okay. So now take this variation, delta variation. If delta variation of this term, but we know that delta variation of this term is equal to 0 if it satisfies this Euler-Lagrange's equation d by dx del f by del y dot minus del f by del y. Here f is equal to sum over j pj qj dot minus h. So what is the equation should be like this: d by dx del f by del qj dot minus del f by del qj. Now calculate del f by del qj dot, it will be pj del f by del qj minus del h by del qj from that function. Putting that del f by del pj dot is 0. So we got this equation del f by del pj is equal to qj dot this, and pj dot is equal to minus del h by del qj. Okay. Pj dot equation represent canonical. Okay. Qj dot is equal to del h by del pj, and pj dot is equal to minus del h by del qj. These are the canonical equation. Okay. Hello.
Yes, sir.
Okay. Okay, we'll discuss in the next class other things. Huh? Okay, I
Yes.
think I cannot take your class Monday, Tuesday. Instead, I may take on next Friday. Okay.
Okay, sir.
Okay.
Monday to Thursday will be off.
Monday, Tuesday off. I cannot take my classes. If other classes they may take, I may take.
No, your next
Maybe
week will be Friday.
My next class is on next Friday. I think 25th. I will take a class 25th. Okay.
Okay, sir.
And
So
25th,
timing?
5 o'clock. I think there is no class in 25th, what I have seen. Because 24, 25, 26 at 5 o'clock, we have no classes. Actually, previously it was given to me, but I have some work at that time, but that work was shifted to Monday and Tuesday. So instead of Monday and Tuesday, I will take on that day. Okay?
Okay, sir. On Friday, 5 to 6.
Okay. Okay. Yes. Huh? Okay, I am leaving. I will send the
Yes,
materials.
sir.
Okay. Wait. Okay.